We're continuing with section 14.5, directions with extreme rates of change. Suppose that f is a differentiable function of two variables and u is a unit vector. The directional derivative of f at a and b in direction u is greater than f at a and b dot u. But what is the dot product? Dot product is over here is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. Wait, magnitude of the second vector, that's just the magnitude of a unit vector, and that's equal to 1. So now you have the magnitude of the gradient times cosine theta is the directional derivative in direction u. Now, what is interesting for us, let's say in the field of data science, for example, what you're looking for is you're trying to minimize error. And you want to minimize error fast because you're using some numerical method and you have to go in a direction that minimizes errors fast. And so what do? You find when the directional derivative is basically decreases fastest, or sometimes you want to maximize something fastest, and so you go to the direction that directional derivative is the highest. So when does this happen? Look, all the trick is on that because that value is the same for all the directional derivatives. The entire thing depends on cosine of theta. And so what is going on with cosine of theta? If cosine theta is equal to 1, the directional derivative is the maximum. If cosine theta is equal to -1, the directional derivative is minimum. Or if cosine is equal to theta, f is increasing fastest, and if cosine theta in that direction, if cosine theta is -1, then the f is decreasing the fastest in that direction. And so all depends on theta. And if theta is equal to 0, then cosine theta is equal to 1. If theta is equal to pi, then cosine theta is equal to -1. Oh, by the way, 0 and pi. So the angle between u and gradient, between the gradient and u, we're talking about either being 0 or pi. That means that the direction that the increase and decrease is happening, the fastest increase and fastest decrease is happening, is either one is direction of the gradient, the other one is the opposite direction of the gradient. So the gradient, a gradient of f points in the direction that f is increasing the fastest. And then all this story was that the negative gradient is the fastest decrease, basically. And so the negative direction of the gradient points to the fastest decrease, or in the value of f, basically. Then the directional derivative is 0 in any direction orthogonal to the gradient of f and a and b, the gradient of f at a and b. And that's something else to remember also. If you don't want any change, if you want to stay on the level sets, you stay on the in the direction orthogonal to the to gradient of f. Now, Directions with extreme rates of change, and let's do an example. A metal surface S is shaped like the graph of z equal to 2x squared minus xy plus 4xy squared minus 3y. A marble is placed on the surface at the point P1 and 1 and 2. Part A. Part 1. Which way does the marble start to roll? Okay, wait. How does this relate to what we just said? This is how. If I know the direction of the gradient, then I know the fastest direction that the z is decreasing is the opposite way of the gradient. And so universe knows this, and how the gravity works. The marble is going to try to go through the direction that is the fastest decrease in height, basically. And so first thing you do is you find the gradient vector. And the gradient vector here is 4x minus y plus 8, and then minus x plus 8y minus 3. You plug in the point xy of the point, because 2 is the just z value in the function. And then you find the gradient at point 1 and 1. The direction -3 and -4, or you can show it in the unit, is the direction that the marble starts to roll. And part 2, find the horizontal tangent line to S at P. Horizontal tangent line is when basically it's the direction that the directional derivative is 0. Now, gradient of f is basically that means that the gradient of f is perpendicular to that direction. And so we have to find that direction, or so there could be multiple ways. And how do we find a perpendicular direction to the gradient? Look at this, it's -3 and -4. What could I dot product with that to get 0? And that would be, let's say, 4 and -3, or it could be -4 and 3, or any multiple of those anyway. So that's the direction that we go, and then to get the horizontal tangent line. And that's when the horizontal tangent line also means that z is not changing. So for x and y, that's the direction, that's x and y. 4 and 3 is the direction, and z doesn't change. So the line, actually the directional vector for the line is 4, -3, and 0. And then you have a point on the line. When is the point? Point is 1, 1, and 2. So you get the equation of the tangent line, horizontal tangent line. I could hear question 14.5b. The temperature at a point xyz is given by T of x and y and z. Heat is radiated outward for a fire burning at the origin. Which of the following could equal a gradient of T at 1.1, 3, and -2? So maybe pause and think about it and come back. Okay, the question is saying at point, what is the point? 1, 3 and -2. So 1, 3 and -2. Here's the point. It's in the fifth quadrant, basically. So at that point, what is the gradient? And so the gradient is directing us to the fastest, basically to fastest increase in temperature. And so now, which way is the fastest increase in temperature? Basically going inward in that direction, right? And so it can be outward, because outward is decrease in temperature. So what would that be? That would be, if you look at this, the x and y is going to be negative value, and then and z is supposed to be a positive value, and that is b, basically. So it's the 1, 3 and -2 is the direction outward, and then you want to find the direction inward, which is -3, -3